is this, the expectation of x and y. So mainly, this tells you the correlations between x and y and the relationship, right? This tells you roughly the relationship between x and y and how it behaves. So now there are certain properties that you can show, and I'm going to leave this as in your spare time before you go to bed, right? So these are interesting exercises that you can show in 2 lines. Now, let's talk briefly about the concept of being independence and the correlations. Okay, if I have a jointly distributed x random variables x and y, and if I take the integral over all y, then I have the marginal PDF fx. Okay, so and if I take the integral over all x, then I have the marginal PDF fy. Now we say that x and y are statistically independent when this PDF can be written as a separable function. So you can write fx of x times fy of y. Now in this case, it means that x and y are statistically independent. They don't have anything to do with each other. Now a more relaxing constraint is called uncorrelated. Okay? So when you take the expectation of x and y, okay, as in the previous slide, and if you can show that it's the same as expectation of x times expectation of y, then it's called uncorrelated. So you can easily show independent will lead to uncorrelated, but I cannot show otherwise. I cannot start here and try to get there. Okay? So this is a more relaxing constraint and in practice, all we need is actually this. Okay? As long as we can say that they are uncorrelated, then it's okay. Now another concept is orthogonal, but we rarely use this. I just put it there for reference only. So these are the same with zero mean random variable. Okay? Too much information, right? But you've seen all these, right? So it's just a brief review so that everybody on the same page. Now a random process is a collection of random variables. Or you can think of a time-dependent random variable, a random variable that has a time component. Okay? So we need n-dimensional joint PDF to characterize x of n if you have n components to it. Okay? Which is becoming very, very difficult. Okay? So we rarely can say anything much about random process. The only thing we can but random process is very important in our study, right? Because, for example, speech, music, or images, video signals can be treated as a random process. You have a bunch of pixels or samples, right? Each of which can be treated as a random variable, and a collection of those form these signals, right? So it's a random process, and we need to come up with a way to study these random processes without having to deal with the n or infinite dimensional joint PDF function, okay? Which is impossible to describe. Another example would be a sequence of binary numbers transmitted over a communication channel. It's also a random process. Or the temperature x of t outside campus, okay, for any given t. That's another random process. Now, since we cannot deal with the n-dimensional joint PDF because it's way too complicated, as engineers, we come up with a way to simplify what we're trying to say. So we come up with the concept of Y-sense stationary, okay? And as far as image, speech, audio, images, and video go, this is as far as we can go, okay? Because this is the only way that we can say a little bit about the signals, okay, using the concept of random variables and random process. So a Y-sense stationary random process is the one for which the expectations of x of n is independent of n, okay? So it has the same mean throughout, and the expectation of x index m and x index n only depends on the difference m and n, only based on the difference. How far you are away, how far m and n are away, and that's it. That's the only relationship that we care about. Okay? So the mean is defined as this. Autocorrelation is defined as that. Rxx of k is defined as the expectation of xn and xn minus k. So see, this is a function of k because the only thing we care about is the difference between the index. Okay? We don't know anything else to say about this random process except that. Okay? And then you can come up with various other properties. Okay? So for example, expectation of x squared or the variance of this random process, so on and so forth. Now, so maybe the most vivid or the most popular use of Weissan stationary random process is the way we model noise. Okay, the way we model noise is the best way that I can describe a Weissan stationary random process. Okay, so basically noise means this. Noise means that is when you take the Rxx of k. So first of all, it has to be a Weissan stationary random process. Okay. Second of all, you need Rxx of k to behave this way. What does this mean? What does this mean? What is Rxx of 0? Rxx of 0 gives you sigma x squared. Okay, so that's the expectation of between you and yourself, right? So certainly it has something to it. Okay, but then when you take Rxx of 1, what does that mean? Rxx of 1 means the correlation between you and your neighbor. The correlation between you and your neighbor, right? Right? And that comes out to be 0. Meaning that you have nothing to do with your neighbor. Okay, your neighbor doesn't have anything to do with you. You're totally different. There's nothing we can say. Okay? So that is a white, zero mean, Weissan stationary random process. And if you plot the, so if we define the power spectrum of a Weissan stationary random process as the Fourier transform of Rxx, and when we plot it, we plot this. Okay, we take this through the Fourier transform. You study Willman, right? Put it through the Fourier transform, you're going to show that Sxx look like this. Okay, now, which means that in frequency, okay, this noise has infinite frequency, and it has the same signal energy on all frequency. Okay, this is quite powerful, right? So this is the worst case that is as far as compression goes. This is the worst things that you can ever expect to see. If you have white noise, forget it. There's just nothing we can do about it. There's nothing that I can predict. Okay? So let's take a break now. And then when we come back, okay, we'll talk about, no? About right? It's okay? Okay? And feel free to say that I'm too fast, too slow, speaking too low, to whatever. Okay? Now let's finish up. I only have 2 more slides, and we finish up this introductory part, and then we move on to variable length coding, lossless coding, and decoding. Okay? So this slide, I want to show you the way we model our image video signal using stochastic process. Okay? So the model that very popular, right? That we've been using for the last 30 years. Okay, is something we call AR-N model. Okay, AR stands for auto-regressive. And what it means is just this: you take white, zero mean, Weissan stationary Gaussian noise, okay, which is W of n, and you feed it through a filters, right? This is a digital filters, right? You recognize this, right? This H. So you can do convolutions. However, this filter is interesting. This filter is not FIR. This filter is IIR. This filter has poles. They don't have